Example 2 says, for what values of x is the linear approximation accurate to 0.5? So we have our function f, and then we have our linearization L, and near the point 1, 2, okay, or for x close, for values of x close to 1. You know how the y values give you an overestimate of the real y value. This point will give you the real y value, and this point, this y value would be the approximation. Y is an approximation. So where was I? Okay, so you want the space between those two, or the distance between those two, 0.5 or less. Okay, now in this case, you know the linearization is greater than the real y value, but you may have cases in which the function changes like this at this point, and then the tangent line may overestimate, like in this case, or may underestimate, like is in this other case. So always just keep that in mind, whether it overestimates or underestimates. So in this case, we know that in both directions it overestimates. So you know L would be greater than F around 1 for both cases. So the book is showing you a way of finding this out. Remember that whenever we talk about distances, we talk about absolute value. So this is F, and this is minus, this is the linearization L. So you want the distance between those two to be less than 0.5, because it could go either way. It could be that the function is greater than the linearization, and you still want both of them to be away 0.5, no matter which one is on top. So you know that from absolute value of an inequality, this can split up into two inequalities, at which I have what I had at the center still stays there, and then less than 0.5 or greater than the opposite of 0.5, which is negative 0.5. So what this means is the subtraction of those two y values has to be between negative 0.5 and 0.5. So this is the equation that I'm going to graph on the calculator, unlike the book is showing you to do something extra. So I have this y minus this other y, and I'm graphing the functions 0.5 and negative 0.5. So this is what I'm going to see when I graph them. Now, because I have these two equations with low y values, my window, I'm going to keep it between negative 1 and 1 for y. For x's, it could be, you know, negative 20 or 20, or negative 10 or 10. That would be fine. So I get this. So as you notice, the difference, because I put the function first, if I put the function first minus the linearization, I know the linearization is overestimated, so this number is going to be always negative. So that's why my graph is on the negative side. So although it does not intersect on the positive 0.5 here, it does intersect at y equals negative 0.5 for these two x values. So those are the x values for which within this domain, the difference of the real y and the approximation from the linearization is between 0.5. So I'm interested in finding what these two x values are. So again, I'm going to go to calc, and I'm going to use intersect, and the calculator is going to ask me for the two functions that I want to intersect. This is the first one, and then the second one is not 0.5 because there's no intersection with that function, it's with the one in the bottom. And then my guess, I can move my guess here because my guess is a blinking dot here. I want to guess first this x value because I noticed that there's two of them. So I'm just going to move with the arrows closer to that particular point that I want, and then the intersection will be x equals negative 2.656. So I'm going to write that down, x equals negative 2.6569. Okay, to be safer. And then I'm gonna do the same thing again because I wanna know where do they intersect again. Oh, first curve, yeah, that's the one. Second curve, y equals negative 0.5. And then my guess, I'm gonna move the blinking dot closer to the other one because I want the other one to be found. Now intersection here, it says x point 8.6569. Okay, 4 decimals is fine whenever I have that. So what does that mean? That means that if I really zoom in, okay, so I have my function and I have the tangent line right here, and this is the point that we were studying, 1, 2. That means that whenever x, this is x equals 1, whenever x is between here's my y value, between negative 2.6569 and 8.6569, between those x values, the difference between my approximation and the real y value is less than 0.5. 0.49 or 0.9999, and in here the same way. Okay, so for all those x's between negative 2.6 and 8.6, all the difference, the space between the tangent line and the function itself is less than 0.5. That's all it means. Now, that's if you want to be accurate within 0.5. If you want to be accurate between within 0.1, then definitely the x values that you're going to have, the interval that you're going to be able to use is going to be a lot less. Like if I want to be only 0.1 away from my graph, then definitely the interval around 1 is going to be a lot smaller than the one around 0.5. So if this number is less, then you're getting closer, you're closing in to 1. So try to do the one for 0.1 accuracy for yourself. In this case, since I already put f in here, I just need to change those values to 0.1, negative 0.1, and see where they intersect. And again, probably, well, I'm gonna change my window because now 0.1 is, everything is just too clumped in there. So my y minimum, maybe negative 0.5 would be better. So now I can see that's y equals 0.1 and that's equals y equals negative 0.1. So now I'm gonna intersect those, first curve, second curve, and my guess. So this x value now it's negative 1.1298, and then I can do that again. 5. That's the first one. That's the second function, my guess, closer to that intersection. So now the other point where they intersect is 3.9298. So as I had predicted, as I had predicted, now the interval for which you are 0.1 away from the real value is negative 1.1298 and 3.9298. So now you're closer to 1, therefore the difference of the approximation and the real thing is definitely less. This is something that I have encountered often whenever I read physics books or even biology books, whenever they say we're going to approximate this, I don't know, blank, to this blank blank equation to make things easier. So this is something that I have seen before. This formula is being replaced by simply negative g theta whenever you say that theta is small, meaning around 0. So that is very good news, that instead of having a function that varies like this calculations are a lot faster if you have an equation that just looks like this rather than having a trig function. But why is this equivalence possible? Well, that's thanks to linearization. So don't forget to be thankful before Thanksgiving for linearization. Include it in your prayer at the table, and your parents will look at you thinking that you're crazy. Anyhow, so what would be the linearization? I can't spell anymore. Of sine of x at 0. So what is that? So L of x equals f of a plus f prime of a times x minus a. So let's see what that turns out to be. So the linearization is f of a, that will be sine of 0. How much is sine of 0? That's 0. Now the derivative of sine is cosine. So that will be cosine of 0, which is 1, times x minus, how much is a? 0. So linearization is 1 times x, that is x. So if the function is sine of x, then its linearization is simply x. Isn't that something? As long as x is close to 0. Because if it's not, then this linearization is way too off for this. I mean, you can never say that a trigonometric function like this is the same as a linear function like that. Like, you can't say that. But around 0, they are close enough. That's what you're saying. So what would be the linearization for cosine? Let's see. Linearization for cosine, f of x is cosine of x. So f prime of x will be negative sine of x. So those are facts. So now let's apply the formula. F of 0 plus f prime of 0 times x minus 0. That's what I'm trying to find. F of 0, cosine of 0 is 1. F prime of 0 would be negative sine of 0 times x minus 0, which is x. Now you know that sine of 0 is 0, so sine of 0 is 0 times x, that disappears, so 1 plus 0 equals 1. That's why the linearization of cosine around 0 is 1. Remember that cosine looks like this, so around 0 it looks like a flat line going across 1, but only around 0. This function and this function, they are not the same.